It's my pleasure to introduce our own Professor Majid Zamani. Majid joined our faculty in 2019 and was promoted to a tenured associate professor in 2022. Before that, he spent about 5 years on the faculty of the Technical University of Munich, or Technische Universität München, if you're doing it right. And he earned his PhD in electrical engineering and master's in mathematics from UCLA. And that followed both a master's and bachelor's in electrical engineering in universities in Iran. Majid has an amazing record of accomplishments, honors, awards in his field of cyber physical systems, and I could either recite them now or let him have that time for his talk, so we'll do the latter. So as you can see, his talk is on proofs from data, certified control for cyber physical systems.
Thank you, Bobby, for the nice introduction. And good afternoon, everyone. I'm glad for you being here. So hopefully I'm able to convey some of the research we've been doing in the past many years in my group, mainly around the certified design of cyber physical system / autonomous system, right? I interchangeably use these two keywords throughout my presentation. So, yep. I mean, of course, for this audience, I don't need to explain why we should care about CPS. I mean, as you know, CPS are on the rise. These are all examples of cyber physical system, by the way. We have automation, traffic networks, self-driving car, and power grid. They're becoming more and more ubiquitous, and we know why, because computations are becoming cheaper, communications are also becoming cheaper, and the systems are becoming more complex. So, and at the same time, they're also exhibiting more complex behavior because we are integrating these components together, computation and the physical part. So they are tightly interacting with each other. And that's cause for this system to actually exhibit complex phenomena, behaviors. And in many scenarios, we cannot actually model the dynamic. For example, you are given a very complex Simulink model in MATLAB, and that's the model you have. And it's not very easy to come up with an abstract mathematical representation for that system. It's very hard. Or the company doesn't want you to know. The only thing you get is a black box model. You can interact with the black box, provide input, get output, but you cannot see inside of it, right? So, and of course, we would like them to be autonomous, right? That's the goal. So hence, underlining the need for safety for these systems. And the other thing which is becoming more and more interesting is due to advance in sensing and memory, they're becoming also cheaper. We have access to large amounts of data. So the question is, can we leverage those data in our advantage and design these systems in a certified manner? So what is happening today? A state of the art in industry, predominantly these systems are designed using heuristic approach that pose challenge, of course, can lead to catastrophic events, right? The very usual suspect example I always present is the Uber fatal crash in 2018 in Arizona. And the reason I am very keen to represent this example is because the crash was totally avoidable by the safety mechanism in the Volvo car itself. The camera detected the person perfectly in time. So a normal control algorithm should have actually prevented this crash. And look at the reason. The company's self-driving software wasn't designed to expect that the pedestrian outside crosswalk may be crossing the street. So, and that was according to the investigation. So when we design a controller, for those of you who are familiar with, for example, temporal logic property, we always say, always avoid collision. And that's why we always say, always avoid collision. No matter what, you always should prevent collision. So, okay, so let's do testing, right? What is the problem with testing of autonomous systems? Of course, the pros of testing is they're very efficient in identifying straightforward cases. But the cons is they can be costly. In China, they have a dedicated road for self-driving car. human-driven cars are not allowed to be in that road, and they can be also dangerous. This is another accident happened in 2023 October in San Francisco by Cruise self-driving car. And again, the same thing here. The camera detected the woman underneath the car. The car decided to drag the person. And all of you know what happened to Cruise. GM canceled the whole autonomy division after several incidents, but the most important one was this one. So same thing with Uber. After that crash, also Uber canceled the whole self-driving division. So, okay, let's look at some statistics. So in US, we have 1 fatal crash per 100 million miles traveled. By the way, this is including drunk driver. So, okay, let's say we would like to reach to the same confidence, but let's say we want to do tests at a rate which is 10 times longer than this mishap rate. So that means we approximately need 1 billion miles of testing, right? Okay, what does it mean? We need 25 round trip on every paved road in the whole world to reach to the same level of confidence we already have for human driver inside the US. So, and we are only allowed to have 10 critical mishaps during those 25 round trips around the world on every paved road. And guess what? If you update your software, every test you have done, you have to do from scratch. Every guarantee or empirical guarantee you gather doesn't work anymore. If you go and change your neural network parameters in your self-driving car, you have to go and change the whole test again, meaning everything from scratch again. So as you can see, brute force testing is not practical. So is this just a theoretical concern because we would like to publish? No. In fact, standards are also pushing for that. It's not only for academia. So, I mean, of course, mainly in EU, but I would say also in US is going to happen. These are 2 standards recently published from EU, which are asking for formal verification and formal methods in designing autonomous systems. ISO 26262, which asks for functional safety. It's a risk-based safety process with method-dependent verification and validation obligations. So formal verification is highly recommended for architecture and unit design. The other one is called SOTIF, which addresses safety of the intended functionality. Requires a structured safety argument supported by appropriate design, verification, and validation measure, which is a natural fit for formal specs, model checking, proof, and falsification evidence. So takeaway is regulators and standard bodies, they also expect rigorous systematic assurance for designing autonomous systems. So, and in fact, nowadays, if you go to all of these, I mean, not that many of them left, but the remaining self-driving car company in US, if you check, they are now asking for people who are familiar with these keywords in their job descriptions. In fact, they're also asking people to be familiar with this type of a standard. So this is what the company also, they're realizing that they should hire people who know rigorous system design, they're familiar with formal verification and formal methods. Okay, so this is about the motivation behind my talk. So now you might ask where my research lies in all these things. This is where my research lies, right? We have autonomous systems. We collect information through the sensors. We actuate the system through the actuator. And of course, what lies here is a software which is controlling your physical system. The question is, how do we design that software? With formal guarantee, with proof. I would like to design that software, and I would like to have the proof that if I implement this software and apply the software, let's say the autopilot, I want to do adaptive cruise control, for example, right? Or lane changing. I would like to give you formal guarantee. I would like to give you the proof that my software works with 100% guarantee. Meaning that if I tell you there is no collision, I have a proof for that. Mathematical proof is not based on scenario which I have seen in the past. It's actually a proof that even works for unseen scenarios. So, of course, in the context of CPS, requirements of interest are usually in the form of temporal logic. And what is the main goal is, either you can give me the autopilot software and you ask me, hey, Majid, can you verify my software works properly? Then I can do that for you. I can formally show that your software works properly with guarantee, meaning that your closed loop will satisfy the property of interest. Or you might ask me, can you design the software such that my autopilot works correctly? What is the challenge? The challenge is, I mean, this is very dynamic, right? It's very complex. I have a continuous space, dynamic here, very complex, this tight interaction, and also I might not know this map F to begin with, right? Why? Because the industry is not interested to disclose that map F. Or they might tell me, hey, this is too complex. We're not going to give you a mathematical object you can work with. The best thing we can give you, we give you a software, you can interact, provide input, collect output, use those input-output to design the software. That's the best thing I'm getting. So the question is, can I use the data that comes from this map F to design the software here such that this closed loop satisfies the property of interest with formal guarantee? I want to give you the proof. And that's why I said proof from data, right? So one method which has been introduced in the community since 2004, and George Papas, they are pioneers in this technique, is they say, look, what you can do is try to discretize your system, make it discrete, fully discrete. This is an infinite system, by the way, right? This is an infinite, it's an uncountable system. So this dynamic, in fact, captures infinite memory. So you can make it finite, and then try to actually do all the formal guarantee in the finite domain. And then you might say, why we want to do that? Because things are very systematic up here. When you have a finite object, you can actually apply algorithmic machinery from, formal methods community in CS, and you can actually run the algorithm, it terminates, it gives you an object, and it gives you the proof that this object is correct, meaning that if you apply this controller, which is in the form of a finite set machine, over this finite object, you know that this interaction is correct, and it satisfies the property you requested. And then the final phase is, of course, I cannot apply this over this infinite space system, so you need to refine it to something which you can apply here. The good thing with this diagram is all these steps comes with guarantee. There is a guarantee going up. There is already a formal guarantee here. There is a guarantee coming down. If I apply this, to make it easier, this is how my autopilot look like. It's a hybrid map. This is my software, by the way, high level. Mathematically, this is my software. I apply here. My autopilot works, and I have a formal guarantee over it. So, of course, I will show you the drawback of this method. But it's very systematic machinery. I like it myself, and we use it in the lab as well. So what is the main ingredient in this approach? Is called reachable set construction. Approximation over approximation of reachable set of your dynamical system. This is the main ingredient, literally, in the previous approach. So what do I mean by that? If my system starts from a continuous set, let's say this is a square, if I apply an actuation to my system, where do I land? Give me a set containing all possible behaviors of my system. And this is what I mean. We do not, when we provide guarantee, we provide for all possible cases. And that's why we can handle corner cases which people in industry, the testing cannot handle, because we capture all possible behaviors that system can exhibit by computing over approximation of reachable set. And that's why our method is formally correct, because we literally give you all of it in the form of this continuous set. Everything your system can show in 1 unit of time is going to be inside here. That's called the over approximation of the reachable set. And then what you do when you build the abstraction, you just put transition to all the cells that intersect this. You see, we introduce non-determinism because we want to be on the safe side. I am introducing a spurious transition because I would like to be on the safe side, right? I don't want to miss any corner case. I am introducing even more, right? That's what's happening here. And then you repeat this, you have a finite system, and now you can actually do verification or formal synthesis. You can design a software, or you can ask a question of, if my system's safe, yes or no. You can apply algorithmic machinery, and then you get the answer. Of course, for computing this so-called over-approximation of the reachable set, the whole idea in all this paper was, you have the map F, this map F here. The question is, what if you don't have it? How do you compute that object, the reachable set? Can we do it? The answer is yes. If you have some assumptions over your dynamic, by the way, there is no free lunch. You cannot just say, I don't know anything about my system, but I also would like to provide formal guarantee. That doesn't work, right? You need to give me something. Okay, what is that? Give me some regularity property of your system. For example, it is Lipschitz continuous, right? That's enough for me. And give me some bound over that Lipschitz constant. I can use that information to actually build this finite system without knowing the model of your autonomous systems. I'm not going into the details. You can find the details in this paper. So, but then you might say, what if I don't know Lipschitz constant? That's okay. Give me noise, give me nothing, right? I don't need anything. But then I don't give you 100% guarantee. I give you guarantee with some confidence. If you're okay with probabilistic guarantee, so now I say, rather than giving me the Lipschitz constant, do not give me anything. I can still build the finite representation of my autonomous systems. But in this case, if I, let's say, I would like to design a collision avoidance software. What is my guarantee at the end of the day? I said, look, you will not collide with the obstacle with the probability of at least 99%. I mean, of course, you can adjust the probability. 1 minus 10 to the power minus 5. If you're happy with that, then you use this method. If you want 100% guarantee, then you should give me something about your system. So, I mean, it's now your call to pick which one you're happy with. So we have a tool that you can actually apply all these methods in it already, even if you don't know the map F using data. And this is a setup we have in the lab. This is the model of this car. I'm not going to use the model for controlling the car. I'm going to use it to collect data, right? So that means I put this inside a black box. I can access it using data, but I don't use the map F explicitly. Here, the car is supposed to go to the green region, avoid red obstacle. And the student comes and introduces obstacles which were not introduced before. So the car is able to navigate in real time, choose the correct action. So we start, within one of our NSF projects, we start collaborating with Norwegian University of Science and Technology, UC Berkeley, and Hong Kong University. And they said, this is interesting. We would like to use this, finite abstraction-based idea to actually control a docking of a surface vessel. We said, we have a surface vessel in our lab, and we would like to use this, finite abstraction, reachability base, even though we don't know the model. They wanted to apply and see if it works. So, and this is the video of so this vessel is supposed to avoid those obstacles, the yellow obstacle, and supposed to go somewhere there and dock. So, I mean, You see, it works as long as the systems are not very, like in terms of dimensionality, are not very large. We can use this machinery of computing over approximation of reachable set, building this finite representation, design a controller, apply the controller, and it works. Even if we do not have access to mathematical representation of the robot. Okay. Now the question is, but this discretization of the space can be challenging. If you are dealing with large scale system, I mean, you're going to suffer from curse of dimensionality, right? I mean, how big of a system you can handle. Sometimes you might need like 10 to the power 12 of, discrete state. And now imagine about the memory size you need. We realize, okay, this might not be practical all the time. For a small system, it's perfect. For larger system, might not. Do we have another proof rule for the safety verification? The answer is yes. I can actually use a function as a proof of my system being safe. I mean, I'm going to explain it very briefly. I'm given a system, which is a CPS, x plus equal to f of xw, represented by this recursive map, f. So now my question is, if my system starts in the green region, the question is, can I formally prove that it never goes inside the red region, right? Let's say the red in your context means colliding with the car in front, with the ego car, right? So, okay, how do I prove that? And this is the dynamic of your vehicle. Okay, proving this property boils down to finding the function b that satisfies these three properties. If I'm able to find a function b that satisfies these three properties, that is your proof that your system is safe. Meaning that if you start in green, you do not go in red. By the way, when I say proof, don't think something very complicated. Here, existence of that function b is your proof of safety. So now your task is to search for that b, the function b. So, okay, how do we search for this b? If I know the map f, meaning that the mathematical representation of my car, so I can use some optimization technique to search for the function b, right? For example, if f is in the form of polynomial, then there are some convex optimization technique which I can use to search for the function b. But these are not complete approach, meaning that you might search and you might not find anything. So that means then you cannot say anything about the safety, right? But look, in order to search for b, I need to know the map f, but I do not know the map f, right? Because I'm given a black box representation. I don't know f, but still I have to search for b. So that's the question. So this is about verification. I want to verify system start in green, doesn't enter red. Of course, I can also talk about design of the controller, meaning that in the case of collision avoidance, I would like to design a adaptive cruise control. So of course, there is an actuation involved as well, right? So you see the last condition only changed. The first two conditions remain the same. The last condition says for any state of my system, there should exist an input provided by adaptive cruise control. No matter what the uncertainty in the environment is, my barrier is my function b satisfies this property. So now in this case, if you can find a function b satisfying these three properties, you have a formally correct adaptive cruise control. Correct, 100%. So again, the search, the formal guarantee or the proof boils down to searching for a function b. Again, to search for b, I need to know the map f, which I don't know, right? Does that make sense? If I'm able to find b, that means I have an actuation for my system that avoids my system colliding with the car in front. So, okay, so now let's see. If I don't know the map f, how can I search for b? So, okay, What I'm going to do is I'm going to cast the search for the function b as an optimization problem. I can always write it, right? It's not solvable, but still, let's write it. So if I'm able to solve this optimization, which is very challenging, by the way, because first of all, I don't know the map F, and this optimization has uncountably many constraints. Do you know why? Yeah, exactly. So your decision variables are q and eta, but look, you have uncertain parameter x, and x lives in a continuous set. You have uncountably many constraints. The map F is unknown. Good luck with solving this optimization problem. Let's say you are able to solve it, and eta comes, if eta is less than or equal to 0, then the b that comes out of this is a valid proof of safety for your system. But now F is unknown. How I'm going to do, that's okay. What I will do is I collect samples from my state set. So you see x now changed to xi for finitely many samples, right? Even though I do not know the map F, but I do have access to its evaluation. Remember I said I can evaluate the system at finitely many points. So I do have that. And this is a linear programming problem. From something very complex, uncountably many constraints I cannot solve, I have a simple linear programming problem, which I can solve easily. It's a LP problem. Many of you have taken linear programming with either Shiram or Saber. So you should be able to solve this easily, right? But then you might say, but wait, you search B and you satisfy the constraint of B for finitely many data points. Initially, I told you that's what industry is doing. They're testing over finitely many scenarios, and I told you that doesn't work. How I'm able to sell this to you? That this B is going to be correct, meaning that this is going to satisfy for every state, not only finitely many points, right? Am I able to provide guarantee for out of sample as well, for unseen data? The answer is yes. What is our favorite, again, tool is Lipschitz continuity, right? If my map F and B are Lipschitz continuous, and I do have access to an upper bound of those Lipschitz constant, then I can actually provide guarantee. Meaning that, come here, solve this. And if you solve, and the eta star from solving this LP problem comes negative, under some conditions over that optimal value, and that condition depends on the Lipschitz constants of F and B, then I can guarantee you that the B comes out of the solving linear programming actually proves safety of your system, even though that proof came out of finitely many data points. It expands everywhere. It also proof of safety for unseen data. Even though it was a proof of safety only for seen data, I can claim it also worked for unseen data. So I can now go to from verification to synthesis, the same thing. This is, this is a control barrier function. I can write an optimization problem, and I might want to try to solve it, but good luck with that. F is unknown. It's actually more challenging than the previous problem because look, you have existential, it's a max-min problem, this one. The previous one was just a max problem, but here is a max-min problem. Max over a state, min over U. I mean, highly non-convex, uncountably many constraints, not solvable. But then we can, again, collect finitely many data. And I do have access to, F evaluated at finitely many data. Here, I assume my input set is finite. So now, the interesting part is, when I solve this, I get a lookup table as a controller. So remember the adaptive cruise control, the autopilot? Actually, the outcome of this optimization is a lookup table that you can implement, and it tells you at every position what should be the steering angle, what should be the acceleration. You just go in the lookup table, search, and it tells you that's the input, apply, and you have formal guarantee. Of course, again, under Lipschitz continuity of your dynamic. Yes?
If you go to the previous slide, aren't you assuming more about f in this case? You have at least access to fxiu for various values of u.
Yes. I assume I need Lipschitz continuity with respect to xi. U takes only finitely many value. Make sense? Yeah. That's a very good question. I don't go into the details of the theorem, but you have a point. Look at here. It's been hidden in the word. Granularity of the data. How close data point to each other should be for that condition, which of course I'm not putting it here because it's very complex, but you are correct. How much data I need actually depends on many things, including Lipschitz constant. And this optimization, eta star n, the value of that, it's going to affect how much data you need.
Is there concern that the physical cases that give these systems problems are precisely the ones that would violate your assumptions? You know, that for instance, the Lipschitz constant is unbounded, growing unboundedly or something like that.
So if that's, okay, your question is, what if my Lipschitz bound, it's not bounded in the actual physical system? Is that what you mean?
Your physical system problems are exactly.
Oh, okay, I see. No, that's not true. I mean, the Uber car crash, they literally in their specification, they didn't say always avoid collision. They assume if the pedestrian, if I am in a street and there is no, crosswalk, there shouldn't be a pedestrian, right? So that is not and also I can tell you, the model of every physical vehicle is Lipschitz continuous. It's impossible to have a car whose dynamic is not Lipschitz continuous. At least they are locally Lipschitz continuous, for sure. Yeah.
You still don't escape the curse of dimensionality with the Lipschitz constant, no matter what you assume as the number of dimensions of your system grows, your number of cells may still be exponential.
Yes, that's 100% true. And thank you for that, because I have a slide that comes to that. But okay, here is try to somehow answer that, but I will have another slide to even answer it better. So what if I don't have Lipschitz continuity? I don't have any assumption about my dynamic. Can I give you something? The answer is yes. I can solve this optimization problem, or let's say for the case of verification, this one, using finitely many n. You pick n yourself. So you ask about n as well. Choose any n you are comfortable with. Solve it. You get an eta. Hopefully eta is negative, because if eta is negative, nothing, that template of B is not good enough. But let's say eta is negative, you choose your n, the n yourself. Now, given that n, I can compute beta. Now I can tell you, your system, you're not going to have any collision with a probability of at least 1 minus beta. And that beta gets calculated using the number of samples you're using. The more sample, the smaller beta. The smaller n, the bigger beta. So if you want to have a very decent probability, let's say 1 minus 10 to the power minus 10, then n has to be very large. I mean, in summary, you cannot escape the number of data points you need, right? So still you need to have a lot of data to be able to provide formal guarantee, either in this form or in the previous form. Okay, now coming back to Shiram's question. He's asking, look, we are not escaping case of dimensionality, correct? Because these are, the red ones are data points, and you see those balls around them? Those balls are supposed to cover every possible case in my autonomous systems, every edge case. That's why I'm drawing those balls. And that's why I need to have a lot of data to be able to cover everywhere. And that's why I suffer from curse of dimensionality. Even in the case of pack-based, when I introduce this probability, still I am suffering. Don't think pack is free from curse. Look, if you want to have a decent probability, 1 minus 10 to the power minus 10, and this is what aerospace industry is using. This is the confidence they have. And look, based on the number of decision variable in your function B, look at the number of data points you need. Even probabilistic guarantee, you do suffer from the curse. You cannot escape the curse, unfortunately. You're stuck with it. But that's good, because you know, human life is in danger and you have to do your due diligence. Yes.
So, I mean, one way of looking at it is in high dimension, even if you have a small probability of not covering something, that accounts for a large volume as the number of dimensions increases.
Exactly. So still. So meaning if you want to, yes. I mean, I give you an example. For example, in many self-driving car company, they are not using the best mathematical model they are using is called unicycle. It's a bicycle dynamic. It's a 3-dimensional bicycle dynamic. They call it like a low fidelity model. It's like a simulation, right? So they use that to generate, let's say, feasible trajectory. And then they use low-level controller to steer the car to follow the, this ideal trajectory. So they are using, in fact, low-dimensional dynamical system, low-fidelity model for generation of safe trajectory, and then they use low-level controller to steer the car to follow that ideal trajectory, right? They do that. And that's the one I showed in the robotic vehicle example we have. That model is exactly what people use in industry to come up with the feasible trajectory and then use the low-level controller to follow that. Make sense? So, okay, now there is a way of escaping from the curse if you ask more from the structure of your system. So you see, now you need to dig into your system property even more. And that's where control theory comes to rescue. Control theory is all about look at your system, a structural property, take advantage of that. And that's very important, right? When you train a large language model or neural network, you ignore all these nice structural property in your system. And the answer is you have to utilize them in your advantage to break the curse. For example, if I have a system which is composed of n components with an interconnection topology, so I actually don't need to look at this system in one shot. I can look at the components separately. I can break the curse, right? Divide and conquer. I divide the problem to the level of subsystem, and then I can do everything I presented. I can go and do it in the level of subsystem. Here, I don't know the model of the component. I don't even know the topology. The only thing I do know is it's Lipschitz continuous, and I do have its Lipschitz bounds. They are Lipschitz continuous, and I do know their Lipschitz bound, and that's it. And I have access to a bunch of data. So the other nice thing I can do, I can actually come up with a sparse M hat. M hat is totally virtual. Come up with M hat, which is sparse, but then M might not be sparse. So I am introducing an error, right? So then use that error to make your over approximation of reachable set even more conservative, because you always want to be on the safe side, meaning that introduce more non-determinism at the gain of having a sparse topology M hat, but then at the same time, you're also providing a method which is sound, meaning that if you conclude anything here, then you can bring it back to the concrete domain. You have the guarantee. So here is also in the context of data-driven. Here is an example just to showcase you can go larger dimension, but if you take advantage of the structure. By the way, we don't know the model. even though I represent, I just wanted to show you it's nonlinear. This interconnection map, it's max, but I don't know it. I can collect data, right? And then we are able to build the abstractions. So, okay, now let's change the gear. What if I utilize more structural property of my systems, namely monotonicity? What if my system has some monotonicity property? You might say, what is monotonicity? Here, if this map F is monotone, what does it mean? For any x prime, w prime, if x is less than or equal to x prime, w less than or equal to w prime implies f of x w less than or equal to f of x prime w prime. If you do know your map F has such property, you don't need to know the map F, but you just assume. I mean, many systems around us, in fact, they do pose that property. Population dynamics, traffic networks, even smart grids under some operating condition, you can assume that the system does have this monotonicity property. Okay, how do we use that? Okay, first of all, this result says the system, which is monotone, is safe with respect to x1 if and only if there is a monotone barrier certificate, the function B. So this is if and only if result. So, okay, now I both the search for the function B, if I know my system is monotone, boils down to finding monotone function B. And now we can take that in our advantage. If I use monotonicity of B, I don't need Lipschitz continuity. I can actually tackle the curse of dimensionality that comes from Lipschitz continuity property. And here I can also provide 100% guarantee, not probabilistic, even though I am not requiring any Lipschitz continuity over my dynamic. This is very important. I still give you 100% guarantee without exploring everywhere. And I don't have a restriction over closeness of data point. And look, result is already good. We can go to dimension 20. We can search for a barrier for a function B, monotone, using only 84 data point. Dimension 20, only 84 data point, I can come up with a proof of safety. If I do know my system is monotone, that's it. In fact, I didn't want to present, but we were able to go to dimension 1000 even with the help of monotone function B. Yes. Oh, actually here we are training a neural network. B is a neural network. And it's a correct neural network. We decided to go with neural network because they are more expressive than polynomial. So far, every time I said I have access to data, I assume I can evaluate F at finitely many data points. But in reality, sometimes you are not given the map F to be able even to collect data. They give you a bunch of trajectory. They said, look, these are the trajectory of the system. Use it to give me the proof. The question is, can I just use pure trajectory? I cannot even evaluate F anymore. I am given trajectory and I'm asked to generate proof. And the answer is yes. Again, under monotonicity property. Here is a simple example. I am given 3 trajectories. And the funny thing is, one of them is not even safe. It starts from already an unsafe region. It doesn't need to be a valid, safe trajectory. I can use these 3 trajectories, and I came up with the proof. The purple area is the proof of safety. Meaning if I start in blue, I always stay in purple. So that means I never go inside red. And this proof got generated just based on 3 trajectories. And of course, under the assumption that the system is monotone. And I don't know the map F, the only thing I do have is 3 trajectories. So, okay, I have 15 minutes left, but given that I already was answering question, I assume I can continue for another 15 minutes. Feel free to interrupt me if you have any question, but I'm going to make it also short. So, okay, yes, I keep 7.5 minutes. So far, the talk was about how to generate the proof, right? But now I'm going to change the gear. How do you transfer the proof? What if you have a simulation and you have a real system? You have a proof based on simulation. How do you transfer the proof to the actual system? Now we are talking about transferring proof between two different domains. To give you an idea, this is the bicycle model I told you people use in industry to come up with a feasible trajectory. Okay, I can use this to come up with a proof. Can I transfer it? And I can use my own tool, Scott's, which we have developed in our lab, to come up with the trajectory for this simple bicycle model to navigate in this maze. Now I'm going to bring it to this car. I use a bicycle. Now I have an actual car. I have a trajectory for the bicycle with the proof. Can I transfer it to the car? Do I need to do everything from scratch, or I can actually leverage the proof I have done for the low fidelity model, bring it to high fidelity? And the answer is yes. So in this work, we showed how can you transfer the proof of safety from low fidelity or simulation to high fidelity or actual system. It's about transfer of proof of safety, right? So in this work, we showed how can you transfer control logic, which is supposed to prove safety, like no collision, for a low fidelity model to an actual car. How do you transfer the logic with the proof? Like how do you transfer the software with the proof itself from one domain to another domain? And then we said, okay, what if the property is not safety? Can we do transfer of logic under any property, right? Just make it property agnostic, specification agnostic. And the answer is yes, we can also do that. I have a source system, low fidelity. I have a target system, high fidelity. And I would like to come up with the control logic for, we call it behavior transfer. Both of them are stochastic, uncertain. So what I would like to achieve is this. I mean, this is very mathematical, but in English it says, if H is the output of my low fidelity, H hat is the output that the high fidelity shows from itself, I would like their behavior to be epsilon close to each other, right? Because you want your high fidelity mimic low fidelity, right? Because low fidelity comes with a proof. So if I'm able to show high fidelity remains close to low fidelity, I am good. But of course, because both of them are stochastic, I'm going to have a lower bound probability on that, right? I cannot show this with 100% guarantee. I show it to you with some probability lower bound. That's what it means, this behavior transfer. And of course, to do so, we need to use some tools which have been developed already in the community. For example, this function V is called a stochastic simulation function that shows the closeness of two systems, and it satisfies a bunch of conditions. But again, we hit the same wall. To find V, I need a dynamic, F and F hat, and I don't have access to those. Both of them are black box, right? So how do I search for V when I don't know F or F hat? I mean, same thing, right? We can, the same thing that I showed in the previous slide, you can collect finitely many data points and you can train V. And you can also provide formal guarantee, right? I have two unknown systems, sigma and sigma hat, representing low fidelity and high fidelity. So if there exists a function V satisfying these two properties, that's a guarantee that I do have a behavior transfer. But how do I search for V? Because it requires knowing F and F hat, and I don't know them. So, but that's okay. You can now train neural network, right? V can be a neural network. And how to transfer the control logic from source to target can also be a neural network. And now you can actually put a condition, and this condition you can guess what is it. Again, depends on the Lipschitz constant, right? If the condition satisfied, happy. Terminate, formal guarantee. You can transfer any control logic from the low fidelity to high fidelity. If the condition is not satisfied, you iterate and iterate. You retrain. Of course, if you reach maximum iteration and the condition is not satisfied, being inconclusive, right? This is what the transferring control under uncertainty is. You train this neural network. This is it's like a translator. It translates control logic from low fidelity to high fidelity. It works as a translator. And this neural network says, okay, it grabs the control logic from low fidelity and it translates it to the high fidelity for you. And you have this guarantee at the end. Okay, so now the last two slides about what I'm going to do in the future. This is what I'm very excited about. It's called accountable by construction. It's an ethical by design of autonomous system. And what do I mean by ethical? So look, you're designing an autonomous systems, but then in the decision making, legally and ethically, in order to have a compliant decision, age of pedestrian and even the pedestrian wearing helmet or not wearing helmet should not affect your autopilot decision, correct? This is based on this literature, right? So meaning that your autonomous car should have duty of care perspective. Do not weigh age difference and do not favor helmet wearers when you are deciding, right? So now the question is, how can I impose such a requirement when I design my self-driving car? So there is a collision happened. Now you're in the court, you have to prove to the judge, because the judge might say, oh, you decided to hit the older person, not the younger one. But then you have to prove that, look, in my control logic, I can prove that if there is a collision, it's going to happen. For any behavior, if the pedestrian would have been an old person, versus if the pedestrian would have been a young person, my control logic do not differentiate, apply the same input. That's how you need to go in the court and argue. And you need to be able to prove that this is actually happening, right? So now this is counterfactual reasoning, right? For any two behavior that my system can show from itself, one pedestrian is old, one pedestrian is young, you have to show that the control logic do not differentiate what it gets applied to the car. And you have to prove that, right? So how do we tackle this? It's, there is a interesting logic out there. It's called hyperproperty. You can actually use hyperproperty to model accountability properties or ethical type requirements for autonomous system. And now everything I explained regarding safety, synthesis, now you have to do it here. Give me an accountable by construction autonomous system. Give me an autopilot and prove it's accountable. So how do you do that? So that's also interesting research direction that we are pursuing now. And finally, we would like to go from theory to reality. So currently we have a ERC project in EU. And as part of that project, we are actually trying to apply everything I explained. First, go into the simulator called Morai simulator, because there we can actually generate realistic scenarios. And we would like to actually put our controller in this NVIDIA Orin developer board. This is a very nice, very capable board, not very big. You can actually put your controller there. And what we are initially trying to do, we are trying to just design a shield. We're trying to have an advanced collision avoidance software, meaning that it goes on top of the already designed autopilot. It observes the input that goes to the system and it shields if it causes harmful behavior. So then interferes and provide a safe action. And we would like to integrate with ACAS with open source stacks like AutoWare Auto. These are all open source. We would like to have some test trials and maybe some partnership with interested industries. And I think that brings me to the end of my talk. Thank you for your attention.
Very interesting and clearly presented talk. Got time for questions?
Yeah.
You're using training the neural networks for finding some function.
Yes. Yeah. Okay, you can, as long as you tell me, like here, this function, I can compute I know it's Lipschitz continuous based on the architecture I am imposing, and I know an upper bound on the Lipschitz constant of it, right? And I can impose that, I can use that in the training because I know my conditions. Because look, at the end of the day, I want to have guarantee, right? And that guarantee boils down to some requirement in the training, correct? So, and in those criteria in the training depends on a bunch of parameters. One of them includes Lipschitz continuity of the neural network itself. So now if you want to change it with LLM or any other models out there, you're perfectly fine to do it as long as you give me that ingredient, which is it has to be Lipschitz continuous, and you have to tell me what is the upper bound over its Lipschitz constant when you are training it. Then I use that in the training cycle. Does that make sense? Then I'm able to use it. Yeah, why not? In fact, I told you, we can use LP, we can use neural network, right? Both of them works perfectly. Or you can use any other functions you want to use. Yes.
About the example, in your future work around the age discrimination.
Yes.
So this looks like an interesting work. Or you're seeing it, but just on this example, this is where I'm a little troubled understanding what gets in that box, which is huge. But why, for example, does the model have any knowledge of age at all, for example?
I mean, I give you an example. I mean, Elon said we have to train LLM, right? They're using all this information of the human drivers. They're putting it in the cloud, and they're training this gigantic model, which is supposed to control the car, correct? So now all this bias from the human drivers goes out there, and now you're training a gigantic neural network, which might favor some pedestrian over others, correct? I mean, look at pedestrian. It has some private feature and public feature. So any bias in currently human driver get translated to that huge model that gets trained, and it's going to be used in all the future autonomy of Tesla. So now your question is, am I able to shield that bias? And my answer is yes. What I can do is I can actually put this accountable by construction on top of that gigantic model. And every time the action is going to violate and it's going to differentiate the pedestrian based on their private feature, I kick in and I give an action which makes it, indistinguishable. Does that make sense?
All the possible ethical issues that you may or may not know about in these very large data sets that you like, how will you surface what is at issue then?
That's a good question. Actually, we start reading this. This has been written by some people in Ford and Law School in Michigan University. And there they were trying to compile some ethical and legal instructions that self-driving car company, they have to follow. So we went and read the PDF. And then for us was, which of those descriptions written in English actually has a formal semantics, something that we can formally describe and use it to design our autopilot. That's where the reasoning came. So when we went read this duty of care perspective was actually mentioned here. And then we try to see, is there any logic that can actually represent that duty of care? And the answer was yes. In fact, we can use hyper properties or hyperlinear topologic properties to formally represent duty of care, which is written in pure English here. Now I have this logic. Now your question is, can you use that logic and design your autopilot to enforce that logic? And the answer is yes. When I design my autopilot, I can ensure you that duty of care, which has been written in English in this PDF, can be enforced in my autonomous vehicle. And I can guarantee that. So meaning that if there is an accident, I can prove that I am not legally violating the duty of care, which has been reported here. Yep.
Or quick, we can probably do it or. No? Well then, thank you again very much.
Yep. Thank you.